Hello, everyone. Welcome to the live session. My name is Matthew. We are excited to have you here. So I'm one of the instructors for the online course, and we are about to have a whole bunch of great questions today. I'm going to hand this over to you, Chris, to welcome everybody, and then we'll get started.
Okay, yes, pleased to be with you again for another live session. We'll sneak one more in before the holidays and then probably take a 2-week break. But looking forward to your questions, so the floor is open.
All right. The very first question for today is it's about from David Gold. How realistic is the implementation of space-based solar power as a renewable energy source?
It's not a bad idea. There are feasibility studies that have been done by NASA and some industry groups. The idea is to use solar concentrators to collect with very large surface areas using ultra-thin collecting material, which has a very low mass, of course, because you have to get it up into Earth orbit, and then it unfurls in Earth orbit. I mean, it's almost as like mylar material, so extremely thin, extremely light. And you can put large areas out there, and then you have to collect it and you concentrate it, and essentially you have to turn it into microwaves to beam it down to the Earth. That's the most efficient way to beam it down to the Earth. So it has to undergo a conversion from the collection of photons into microwave power, and then the microwaves are beamed down to collecting point on the Earth where it can be converted into electricity. So it's a multi-stage process. It's not trivial. None of these technologies are particularly radical or new, but obviously executing it in Earth orbit is quite difficult, and it's probably not economical unless you can deploy an extremely large collecting area, tens of square kilometers, I'm going to guess, because we have solar arrays on the Earth. The only advantage on Earth orbit is that you don't have any real estate limitations. Solar panels and collectors on Earth, use up land resources, and so when they get too big, it can be a problem. Also, some of the radiation is, of course, absorbed by the Earth's atmosphere, so you do get more. You get 100% of the radiation in Earth orbit. It also can be used to collect energy or concentrate energy and then beam it around the solar system or to other places, such as the moon, where we might be conducting economic activities in the future. So as a sort of leading edge technology for the future of exploring the solar system, it also has promise.
The next question is from Lawrence, who is on with us live. Last week you mentioned that neutrinos and antineutrinos are WIMPs, or weakly interacting massive particles. Is it equally difficult to detect each of those, both neutrinos and antineutrinos?
Actually, no. The particle techniques to detect neutrinos and antineutrinos are essentially similar. They each have very low interaction strengths with normal matter. So it's a difficult experiment however you do it. You need large volumes of detectors, ultra pure materials, because essentially only one in an extremely large number of atoms is going to undergo an interaction, and you have to just make that number extremely large and then capture the energy from the neutrino. And if it's a neutrino, it will interact in a physical way by creating mechanical resonance. If it's an antineutrino, clearly it will annihilate with normal matter in the detector and produce gamma rays. So the signal is different whether you're detecting neutrinos or antineutrinos, but they're both equally difficult. And formally, I would say that neutrinos are not considered WIMPs. They're not in the category of weakly interacting massive particles, because although they are weakly interacting and their masses are not completely determined, because of the neutrino oscillation we only measure combinations of the different flavors masses, they are not massive enough, for example, to account for the dark matter fully.
Excellent, thank you. The next question is from Francine Kaplan, who's on with us live. Are there lessons at all that astronomers can use from research at the deepest parts of the ocean? So are there lessons at all from research at the deepest part of the oceans that astronomers can use, and vice versa?
Well, the deep ocean is useful in astronomy in a couple of sort of slightly indirect ways. The ocean is used for neutrino detection. Just had a question about neutrinos, and neutrinos, of course, pass through matter easily, and so one of the methods of detecting neutrinos is by dropping strings of hydrophones, essentially, which detect acoustical energy released by an interaction. And you create essentially a three-dimensional grid inside the water, and you sink these into a deep ocean trench, so pretty far down, deep sea, and then send the signals back up to the surface. There was a prototype detector called DUMAND, that was the acronym, based in the deep trench off the island of Hawaii, and there was a prototype for an even larger detector, which I think is about to be funded. So neutrino astronomy can be done from the deep ocean. And I guess the other way the deep ocean is relevant to astronomy is that is really the subject of astrobiology. It's a demonstration of the fact that life on Earth does not always need sunlight to be viable. So we tend to think of life on a planet as needing solar radiation, of having the sun and a temperature sufficient for liquid water to exist. But the deep sea is a place where sunlight doesn't penetrate more than a few meters through any body of water. And so the deep sea is essentially dark. No light penetrates, and yet there is life there because the energy source is either pure chemical energy or geothermal energy from vents on the sea floor. And so the deep sea floor has been informative for astrobiology to tell us what the range of life on Earth is, and therefore what the range of habitats where we might expect life beyond Earth might be.
The next question is from Keith Crum, who's on with us live, who would like to know if you can give us a few thoughts on the Drake equation. Do you think, I guess he asks, do you think the factor L is the most significant, meaning the length of time an advanced civilization will thrive? Or more generally, which piece do you think is the most significant?
Right. So the Drake equation, I have to say at the outset, it sort of outlived its usefulness. I mean, I've known Frank Drake. He's he's an emeritus professor at the University of California in Santa Cruz. Really nice guy, a titan in the field of astrobiology, and I've known him for a while. And he would be honest enough to say, as he did when he was younger, that the Drake equation is just a framework or a container for ignorance. It was a formalism he invented on the fly as a young postdoc at a Green Bank symposium on astrobiology, I think back in 1960, very long time ago, 60 years ago. So Frank Drake would not overplay the Drake equation, and he's the author of it. And so I'm therefore excused from saying that the Drake equation is only of limited utility in astrobiology. And that's because it's a product of a set of factors which range from the purely astronomical, like the rate at which stars form, to the planetary, the number of Earth-like planets per solar star, to the biological, the fraction of Earth-like planets that develop biology, to the cultural sociological, which is the probability that an intelligent life form develops technology and the ability to communicate in space, and the last factor, L, the lifetime of that civilization. So when you multiply a series of factors, the uncertainty in the product is driven by the uncertainty of the most uncertain term. And since the last three, actually the last four terms in the Drake equation are unknown, the probability that on a habitable planet you get life, the probability that that life becomes intelligent, the probability that intelligent life becomes technological, and the duration in the technological state, those are all completely unknown, then the product is unknown. And at some level, you can't do any better than that. So the Drake equation, definitely has some problems. And other people have recast the Drake equation in different ways or used different pieces of it or homed in on pieces of it. It's a framework for having a conversation. And even some of the parts of the Drake equation that don't get scrutinized deserve to be. For example, there was an interesting paper written by people studying the history of life on Earth who did simulations of how long the habitability of the Earth persists in models of Earth-like planets. And so the lifetime term in the Drake equation is just the lifetime of a technological civilization in the communicative state. But this set of simulations showed that for Earth-like planets in different cosmic circumstances, the random events that can interfere with the evolution of life, catastrophically, like mass extinctions, occur often enough that it is actually very unlikely for a habitable Earth-like world to be smoothly habitable for billions of years. Most likely it gets interrupted. And so the longevity of a planet in the habitable state is a wild card in the equation. That factor is not included in the equation. And recent research is suggesting that all these Earth-like worlds we're discovering, many of them may not be long-term habitable, and so are unlikely to evolve creatures like us if that takes billions of years. So there's a lot of reasons to second-guess the Drake equation. I mean, we're affectionately attached to it after 60 years, and I still use it and I still teach it. But I think we are moving in astrobiology to a more sophisticated way of looking at the issues of life in the universe.
So I think that brings us to a more general question. Can you talk a little bit about what astronomers think about things like UFOs and, especially with the news recently about an Israeli minister talking about UFOs having visited Earth? What do astronomers think about that?
Right. So to answer the really general question of what do professional astronomers think about UFOs, the bottom line is that professional astronomers, it's the bane of the existence of an astronomer, especially one who communicates or educates, because a lot of the general public, a significant fraction, believe that we have been visited by intelligent aliens and that represents the UFO phenomenon. So I guess I would say several things, and I've recently been roped into this because I perhaps naively wrote an article for The Conversation, an online periodical written by university faculty but at a popular level. I wrote about UFOs saying that despite the fact that I don't believe they represent alien visitations, it's not crazy to believe in them because astronomers believe there could well be intelligent life out there. So I think that's the tension for a professional astronomer. Most astronomers are convinced that the prevalence of Earth-like worlds and ingredients for life and the long time over which life could have evolved make it fairly likely that on some Earth-like worlds in the galaxy or other galaxies, intelligent life has evolved, and in some fraction of those cases may have gained technology to travel in space at speeds sufficient to visit nearby stars, for example. So it's not implausible a priori that intelligent aliens that travel between stars exist. The question becomes what evidence would convince an astronomer or any scientist that this has actually happened. And the UFO evidence is generally lacking. Now, I'm not going to make any, firm or unequivocal statements because simply there's such an abundance of evidence that I haven't looked at all. I do know, however, that when people who know the sky look at the reports of UFO sightings, when there's enough information on the sighting that you can say the place, the time, and the orientation in the sky of the sighting, the majority of them are actually Venus. So most UFO sightings where you can say where the sighting was made from and identify where in the sky it was and what time, it corresponds to the bright star Venus. When it's low on the horizon, planet Venus. When it's low on the horizon, it can often appear to hover or move due to refraction effects, and most people are simply not familiar with the night sky. So that's a very mundane explanation for a substantial number of UFO sightings, thousands of them actually. And other UFO sightings are also normal astronomical phenomena. Another subset are high-altitude weather balloons or spacecraft, the ISS, for example, or test aircraft flown by the military, not any particular stealth or strange technology, but just conventional aircraft with a reflection coming off them to the ground. So there's a subset of sightings which persist in down through the literature and online, and now there are videos. It used to be grainy photographs. Photographs can be manipulated. Then it was digital photographs. Well, digital photographs can be doctored. So this is not gold standard evidence to an astronomer, nor are videos. The gold standard evidence to an astronomer would actually be verifiable, independently verifiable, or repeatable, or physical evidence of an alien spacecraft on the Earth. And to me, it's actually striking that of the thousands and thousands of UFO sightings over decades, not a single example of physical evidence has been offered forward to the scientific community to inspect. That's pretty telling, because if there was some strange metallic object that could not be explained conventionally, or that our technology had not been produced and it was available for inspection in any lab around the world, scientists would pay attention and they'd say what they saw. But that hasn't happened, and so eyewitness sightings are just notoriously unreliable. There's a big literature on the unreliability of eyewitness sightings in court cases, for example, where the control experiment is DNA evidence. And DNA evidence has shown that eyewitness testimony is notoriously unreliable. And in a crime case, no different from a UFO case, it's just hard to trust that kind of evidence. Alien abductions, that's a whole different can of worms I'm not even going to open up here. But I think UFOs are sort of a modern religion, in quotes, and they represent a psychological or social phenomenon more than a physical phenomenon.
Kind of continuing our theme of aliens, Vikas Zoli would like to know, let's imagine that aliens attack us from a planet that has 2 times stronger gravity than Earth. Does that mean the aliens would be 2 times stronger than we are?
I suppose if they were biological evolved creatures as we are, the infrastructure of their physical being would be conditioned according to their gravity, so that's probably true. It's fair to assume that any organic biological creature evolving in strong gravity would have strong bones or strong muscles or whatever to sustain itself in that gravity. It's really dangerous or tricky to extrapolate the nature of living creatures in other physical situations, however, because we have such limited experience on our own planet, subject as we are just to the single force of gravity. We don't know how creatures might be if they evolved in extremely low gravity situations, for example. Would that necessarily mean they were big and diaphanous or buoyant? It's not clear that they would be physically very different at all. So these are imponderables of alternative biology.
The next question from Jorge Kitrosser, who's from Argentina. I guess they just had an eclipse, so that's very exciting. The Hayabusa Ryugu material has safely landed on Earth. What time frame should we expect for publication of findings? And can you talk a little bit about the mission and what they did and were looking for?
Yeah, the Hayabusa mission of the Japanese Space Agency had sort of stole the thunder of our local mission here, OSIRIS-REx, which is heading also to an asteroid to bring back material, and captured its material just a month or so ago, but it's a couple of years before that sample will return. So the Japanese sort of beat the Americans to the punch, if you like, with their sample of an asteroid. It's a very exciting mission and a journey of almost 200 million miles. With success, it's clear that they captured sufficient amount of material to make a successful mission, and also they captured gas in the chamber that's sealed and protected as it landed on the Earth. So the sample came, and it was descended down onto the outback into a deserted part of Australia. Large parts of Australia are deserted because they didn't want to risk it hitting anyone or anything, and it was recovered very quickly, of course. And they rushed it back to the lab, because as soon as a sample like that lands, even when it's in a sealed container, there's the danger of contamination, which would ruin the scientific results. So they literally had to get it back to the Japanese lab in sealed vacuum conditions within 24 hours, and I think they managed that. And they've now inspected it, and they know they have a decent amount of material to work with. Some of that material eventually will be farmed out to other research labs around the world, but obviously the local scientists at the host institute and in Japan will get first dibs. And I'm going to guess that they're already analyzing it, and that they'll have a first wave of results within a month. So it's very hot science, of course. And the reason we're interested at all in doing this difficult thing of bringing back material from an extraterrestrial body that far away is that asteroid material is essentially pristine solar system material. It gives us great insight into how the solar system formed. The composition of asteroids tells us about organic materials, the possibility of frozen water or hydrous minerals in there, and therefore the indications of water in a primordial solar system. So, and then there are always geological surprises. So it's going to be very interesting to watch the data come out.
The next question is about an upcoming event. Jessica Gimeno would like to know, on December 21st, do we need a telescope to see the double planet or the conjunction that's happening?
Right. So December 21st, as we've all heard and read, is an extraordinary event of juxtaposition, alignment in the sky between the two largest planets in the solar system, Jupiter and Saturn. Obviously, they orbit in the ecliptic or the plane of the solar system, so on occasion, every few decades, they do appear fairly close to each other. But this juxtaposition is extraordinarily close. They literally are coming about a tenth of the moon's diameter away from each other. They'll almost look like a double star to the unaided eye on the solstice night, 21st. They'll also be visible after sunset in the western sky several days before and after that. But the 21st is the best viewing of them relative to the moon and so on. And they are very close in the sky. To the naked eye, not much to see there. Planets just look like fuzzy blobs, bright-ish in terms of their brightness compared to the brightest stars, but that's all. But to small telescope, doesn't even have to be a big telescope, any decent amateur telescope, 4, 6, 8 inches, will easily be able to see them in the field of view. And of course, you'll have this incredible treat for an amateur astronomer of being able to see Saturn and its rings and Jupiter and probably 4 of its moons, the Galilean moons, in the same field of view. And that's a really extraordinary sight. And that, in that proximity, of course, hasn't happened for about 800 years since medieval times, and it's not going to happen again in our lifetimes. So I urge everyone to go out and at least look at it. And if you can get your hands on some really good binoculars or know a neighbor or a friend with even a small telescope, then it'll definitely be worth looking at it that way.
The next question is from Hassan Azam. Relativity states that light travels at the same speed in all reference frames. Is this true for all waves, like sound waves? And if not, then why is it only true for electromagnetic waves?
Yes, that's a premise of of special relativity. And it is only true of electromagnetic radiation because sound waves are essentially a different phenomena. Electromagnetic waves are coupled electric and magnetic oscillations, transverse oscillations. They're at 90 degrees between the electric and the magnetic field in these coupled oscillations, and they propagate at 300,000 kilometers per second in a vacuum. Sound waves are compression waves that need a medium to propagate, and so sound waves cannot propagate it in a vacuum. They can't exist in a vacuum, and so it's a really different phenomenon. Relativity describes the way light appears depending on your reference frame, and the extraordinary premise of special relativity, confirmed by experiment, is that the speed of light is constant and light arrives or departs at that speed regardless of the motion of the observer. And that's been confirmed amply now. And it's that primacy of the speed of light that leads to the bizarre effects of special relativity, where lengths contract in the direction of motion, where time slows down at speeds approaching that of light, and mass increases for an object approaching the speed of light.
Excellent, thank you very much. The next question is from Mohan, who's on with us live, who would like to know if it is possible that Hawking radiation could be the remnants of a previous universe.
It's an interesting idea. Hawking radiation is proposed but hasn't yet been observed, so it's a hypothetical, it's a prediction from theory from Stephen Hawking, who died a few years ago. It's supposed to be the radiation that occurs because black holes have temperature, and they will therefore slowly evaporate because they're radiating energy and therefore equivalently mass. Now, could Hawking radiation represent the residue of another space-time entirely? That's very hypothetical, and I don't think fits within the theory, actually. I think the conventional explanation of Hawking radiation, if we were to detect it, is that it is essentially a black hole slowly evaporating.
The next question is from Jeffrey Needle. Since we've just been talking about the moon, I'm still interested in what progress, if any, has been made on the Artemis Accords governing space colonization and the utilization of space resources. I'm not familiar with the Artemis Accords, but perhaps you can talk about, what treaties are in place that you know of for exploring and settling the moon eventually.
Right. So the issues of law in space are kind of messed up at the moment because there's no regulatory framework of any kind. There have only been two UN level treaties about space. The Outer Space Treaty of 1965, which banned weapons in space and was signed by most of the world's countries, and the Moon Treaty of 1979, which dealt with the utilization of resources, although it didn't mention commercial entities, and ownership of objects like the moon or Mars. But things have moved on since then, and there needs to be more regulatory framework, or at least understanding, so conflicts can be avoided now that space is becoming a commercial activity. And the Artemis Accords are one attempt to do that. The trouble is, anything to be legally binding would really have to be signed by most of the world's powers, and that's why the United Nations has been seen as the parent body for any new space law framework. And we haven't really come close to any new space treaty out of the United Nations yet. You can also recognize from the history of world politics in the last 50 years that the United Nations is rarely able to work in concert on anything because, for example, for major issues, the Security Council has to have a unanimous vote, and that seems to be quite rare. And then for other issues, you're dealing with almost 200 countries in the world that have to vote on something. Now, most of those are not going to be spacefaring countries. There are only roughly a dozen spacefaring countries now. That number will grow slightly. And they also have trouble agreeing on things because China has different ambitions from the United States, and the United States has different ambitions from Russia, and so on. So I would say the progress on space treaties and the regulatory framework for space activities has been incredibly and frustratingly slow.
The next question is from Robert Donaldson, who would like to know, what areas of astronomy would you like citizen astronomers to support the efforts of research for?
I think because the galaxy world has increased dramatically due to deep surveys, we now have tens of millions of galaxies in catalogs and measured by deep imaging survey. Galaxy Zoo, which is the beginning, the OR citizen science project in astronomy, variations on that and other ways of dealing with that kind of data I think are still valuable. I'd like to see more citizen science projects that revolve around spotting gravitational lensing, which is a rare phenomena. Only maybe, say, 1 in 100 quasars is gravitationally lensed and multiply imaged. So these kind of needle in a haystack but not terrible odds against you projects are very valuable for citizen science. I think another citizen science project, of which there is one in Zooniverse, but I think there could be more, is the search for supernovae, both in nearby galaxies, also in the distant universe, where a supernova can outshine an entire galaxy. So at large distances, you don't see the galaxy, you just see the single light that just comes up and then fades away as the supernova dies down. I think there are other citizen science projects that could be done in planetary science, mapping planetary bodies like Mars, which have been mapped well, but nobody scrutinized in detail all the geological features of Mars for interesting future destinations on Mars or interesting signatures of geological activity or even biology. So these are some areas where citizen science still has some room to grow.
Kathy Donnelly sent an email in astronomy, in our course, Astronomy Exploring Time and Space. Some of the lectures discuss string theory. However, as I understand it, string theory is now sort of out of favor. Has this changed, and how?
So string theory has gone in and out of favor, I would say. It's had a couple of full cycles. At the moment, there was a backlash against string theory that actually peaked about 4 or 5 years ago, with some very prominent physicists coming out against it, or against sinking too many young resources of intelligence and time and career into it, and also some prominent books by well-known physicists against it. because it hadn't delivered on its promise, essentially. So string theory, it's had a bit of a backlash, and that's because at one point physics departments around the United States, I'm not sure around the world, were making about 1 in 5 of their appointments in physics faculty to string theorists, which is a very high percentage for a field that's young and essentially unproven, but very exciting. So I think that was what led to the backlash. There was just too much of a herd mentality following string theory in academia. Now, string theory itself has not gone away. It still retains its promise as a potential way to move beyond the standard model of particle physics and reach for an underlying theory that explains all matter and energy in terms of fundamental one-dimensional entities called strings that manifest on incredibly small scales and at incredibly high energies. I think that idea hasn't gone away, and the consequence of the mathematics that we have to consider multiple dimensions of space and time, and especially spatial dimensions beyond the 3 we're familiar with, I think that hasn't gone away either. So string theory is not dead. It was probably overrated for a while and suffered a backlash, but I think the number of people working on it, the number of meetings I see advertised, the number of papers written is still very strong, and so I would say it's still very active and indeed still a hot field.
A couple people are discussing in the chat the upcoming close approach of the planets and are asking if they need telescopes to see them. I can't remember if we specifically addressed that, but I believe the answer is no. Do you want to mention that?
The basic answer to the question about this alignment is you don't need a telescope to see these planets. These are naked eye objects. The 2 giant planets are easily visible in the night sky, even in an urban setting, maybe not in a bright city center. And so you can see them, and you can see with your eye how close they are together and how unusual that is if you're used to looking at planets in the night sky. To get the extra bonus of watching these 2 objects close to each other and seeing the rings of Saturn and seeing the moons of Jupiter, getting the full symphony of what's going on, yes, you need a telescope, a small telescope.
All right, the next question is from one of our live participants. Samuel Malkin would like to know if you think that we've already passed the great filter.
So let me just back up to what the great filter is. The great filter is an idea in astrobiology. I think it came from a researcher called Robin Hansen, and it was about 10 or 12 years ago, and quite an influential paper. And this is the idea. This is also a partial explanation for what is called the Fermi paradox, or actually more correctly, the Fermi question: where are they? If there are so many habitable worlds and so much time for intelligent life to develop, technology and space travel and so on, why don't we see the universe or the galaxy littered with intelligent aliens leaving their planets and traveling through the galaxy? So the great filter is the idea that in the evolution on a habitable planet, for life starting and then eventually getting to our state of capability, there's some possible hard steps, if you like, to put that in quotes. And they essentially act as a filter, where out of all the hypothetical situations that get to a certain level of maturity, only a very small fraction get past that stage. And so there could be one or more filters in place between life starting and life getting to our level of capability. One of the filters could be the development of multi-celled organisms. So life on Earth was single-cellular, unicellular for over 1 billion years. I think closer to 2 billion years. That's a very long time after life starts before you can get cell colonies and diversification of the function of cells and eventually a multicellular organism. And all plants and animals, of course, are multicellular. So you can get plants and animals without the leap to multicellularity. And maybe that was a hard step because it took a long time. It might not have had to happen at all. Another hard step might be the development of brains. So we think a brain is a vital ingredient of the intelligence to figure out your place in the universe. And even if dolphins and elephants can't do astronomy, we do think they're sentient probably and intelligent definitely. So maybe the development of brains, which also took a long time, it took several 100 million years in the oceans of the Earth for life to develop the sensory capability to detect its environment and then develop the rudiments of processing that information in a spinal cord and then something at the end of that spinal cord that was a processing unit or eventually a brain. Brains grew slowly in evolution over a long period of time, hundreds of millions of years. So maybe brains is a hard step. And then we know that one other hard step is the development of technology itself, because the technology that can get us to the stars is also powerful enough to destroy us, nuclear weapons, nerve agents. And so it's possible that many civilizations that develop some capabilities just destroy themselves, so they never get mature beyond that. They never pass through that last filter. And so that's just a couple of possible filters in the evolution of life on Earth. And if these filters are dominant, or the probability of passing through that stage is low, then indeed we could be alone. And that would be the answer to the Fermi question.
The next question is from Christina Vislapu, who sent an email. Could you please explain more about orbital resonances of planets and moons? How does it work, and what kind of effects do these planetary resonances have?
So orbital resonance is a very fundamental part of planetary astronomy or dynamical astronomy more generally. And it's a simple phenomena of an orbital situation involving two or more objects. Basically, in any situation where the ratio of the periods of two objects orbiting a larger object, like planets around a star or moons around a planet, wherever the ratio of those orbital periods is either a whole number or a whole number fraction, then you can have an orbital resonance. And the easiest analogy which people use to understand this is, imagine pushing a child on a swing. So you have a child on a swing, and you can keep that child going by adding energy to their orbit, if you like, their motion of the swing, by pushing them every time they come to you and then pushing them. Or you could push them every second time or every third time. So you can add energy to the situation of the child's swing period by only injecting energy every time. That's their one period, or twice the period, or three times the period. So that's an example of how you can have coupling between two systems when the ratio of their orbital times is a whole number ratio, or even a fractional ratio. So basically, as moons orbit a planet, let's use that example, at different rates, if their orbital periods have particular ratios, these ratios of whole numbers, 3 divided by 2, 4 divided by 3, 5 divided by 3, etc., then you will have resonance, which means gravitational strong interaction. And that interaction can do several things. In planetary systems, that interaction actually serves to create some no-go zones, because the resonance clears out material at certain distances. And that explains the patterns in Saturn's rings. And it can also occasionally add energy to the point where one of the objects actually leaves its orbit. So you can boost the orbital energy of an object to the point where it moves away from the gravitating object. So there are all sorts of complicated effects that happen with resonance, but the mathematics of it are actually very simple, based on the ratio of whole numbers in the periods of the orbit of the two objects.
Excellent, thank you. The next question is from Nahum, who is on with us live. Oh, I'm sorry. The next question is from Jeff Wolf, who's on with us live. Since the Webb telescope will be at a stable Lagrange point, would we expect an increased concentration of debris to have collected at that point, or will this cause issues?
I think it's a good question, and I think not, for two reasons. First of all, in the Lagrange point where the James Webb Space Telescope is going to go, it's a pretty clean part of the solar system. There's not a lot of debris or leftover material from the formation of the planets or interplanetary particles there at all. So there's not much debris to cause a problem. And the second point is that these are, at the very best, quasi-stable Lagrange positions. There are unstable Lagrange points where, unless the object is being actively guided, it will drift away from the Lagrange point. The quasi-stable ones are not long-term stable. In other words, if an object gains a particular amount of energy randomly over time, it will drift away from the balance point and not return to it. So material actually does disperse from these Lagrange points over time unless its orbital situation is actively maintained, which can be done, of course, for the James Webb Space Telescope.
All right, this next question is from Nam. Is the Hubble constant really constant since early in the universe?
No, the Hubble constant is not constant. So referring to it as the Hubble constant means we sort of benchmark our measurement of the expansion rate of the universe with the current expansion rate, which means the expansion rate now after 13.8 billion years and therefore in the local universe. So when we talk about the Hubble constant, or the capital H with a subscript 0, that's referring to the expansion rate now or locally, the expansion rate we measure from relatively nearby galaxies, whose just light travel times are a small fraction of the age of the universe, so maybe out to 100 million light years. The Hubble constant, of course, measured now, represents the Hubble parameter, which has varied over cosmic time. So the general form is the big letter, capital letter H with no subscript, and that is a parameter that has changed over time. And it has varied in an interesting way, because if we look back at time, we'll see that the expansion rate was slower. And that's the indication that the universe has been accelerating in the last few billion years. That was the discovery of the mid-1990s, essentially implicating dark energy. If you continue to look back before that time, then the sign on the change of the Hubble constant flips to the point where the Hubble constant starts to get smaller again, and that means the expansion rate was slowing in the more distant past and has sped up since then because of dark matter. So the Hubble constant is not a constant, it's changed over cosmic time, and the expansion rate started off very fast, superluminal, slowed down, and then started speeding up again.
The next question is from John Grialva, who's on with us live. Can you explain to me why there is water on the moon?
There's water on the moon because there's water associated with almost every object in the solar system. As far as we can tell and have measured, no solar system object is completely dry. Probably the most bone-dry objects are dead comets, or comets that have traveled through the inner solar system on long elliptical orbits and have passed close to the sun very many times, where the sun has essentially baked them dry. But that's very unusual. Most solar system objects have significant amounts of water. In particular, if you go past what's called the ice line, which is the distance from the sun beyond the orbit of the asteroid belt, where water cannot maintain a liquid form but is in ice, we see the objects as they formed as frozen mixtures of gases, liquids, and rock. And so there's liquid water, but in a frozen form, on almost every outer solar system object, even the small ones. In the inner solar system, that water might not exist very much. Obviously, Mercury has been baked mostly dry, but not completely. Venus is also, it's been hard to retain any liquid water of significance, but it has some. So water exists almost everywhere in the solar system because it's one of the more abundant molecules in the solar system and in the universe.
Excellent. The next question is from one of our live participants. Daniel Geva would like to know, what do you think about the SpaceX Starlink project?
Well, it's a bête noire, as we would say in the French, of astronomers, because the Starlink constellation project is SpaceX's use of low Earth orbit satellites to do an altruistic, not altruistic, they will make money from it, but a generally beneficial thing, which is to deliver high-speed internet to parts of the world like Africa and parts of Asia that just don't have it. They don't have the infrastructure, and they don't have wired internet either. So these constellations of satellites, hundreds or even thousands of them, are in fairly low Earth orbit, a few hundred miles up, low enough orbit that their orbits actually decay naturally, so they deorbit and burn up in the Earth's atmosphere after 5 or 6 years of work, and that's by design. It's planned obsolescence, and then they launch some more. These are designed to be a dense enough network to give internet access to remote regions on the Earth's surface. The problem for astronomers is that these satellites are small, but they're not tiny, and because they're close to the Earth, they appear to be quite large, and when sunlight glints off them, it makes them very bright in the night sky. The typical times when it's a problem for astronomy are just after sunset and just before sunrise, when the sun is making a glancing angle off the satellites and then down to telescopes on the Earth. Large telescopes have done tests of the rather small number of constellation satellites, and they make streaks across deep images of the sky taken with frontier observing facilities. And if people extrapolate what it will be like when SpaceX launches its full suite of what promises to be 42,000 satellites, a huge number compared to what's up at the moment, it's going to essentially ruin almost many, if not most, of the images taken by the Large Synoptic Survey Telescope, for example, at the Vera Rubin Observatory as it's called now, and other large ground-based telescopes. So it's really unpopular with astronomers. SpaceX have made some dispensation to astronomy by experimenting with matte black and other coatings of the satellites to reduce their reflectivity, and initial results suggest that's fairly successful, maybe taking the brightness down as seen from Earth by a factor of 2. But that's not enough to remove them as an irritant and a noise source or contamination on deep astronomical data. So this is an issue that hasn't yet been resolved.
Excellent. The next question is from Ritik, who would like to know, which is better, using an extremely large telescope like the Europeans have planned for the ELT, or a small group of telescopes and connecting them all together as one?
In optical astronomy, there are advantages to one very large telescope. And the simple reason is that the technology for combining separate optical telescopes and getting the benefit of them by combining the data from behind them involves interferometry, which is a difficult experiment to do at optical wavelengths. Radio interferometry at the much longer wavelengths of radio waves is actually fairly easy, and we've done that for over half a century. Optical interferometry with very short light waves is extremely hard. And so even though it seems easier to build smaller telescopes because each one is cheaper, the technology to combine their signals after the fact is extremely challenging, and so far not been as successful as if you just built one big telescope and dealt with the cost of that one big telescope.
The next question is from Jim McLeod, who's on with us live. If you could take us all on a field trip anywhere on Earth to show us a glorious sky or some type of technology like a huge telescope, where would we go?
Well, it's difficult, but it's also easy. It's difficult because I've been to a lot of cool observatories, and some of them are quite special. The one that I would like to go to that I haven't been to is the South Pole. So if I had been there with direct experience, I might pick that one. But of the places I've actually been, I also don't think it's a close choice. For me, it would be the Atacama Desert and the high-altitude observing site of the ALMA, the Atacama Large Millimeter Array, and a set of other telescopes now. This is a spectacular site at about 17,200 feet or 5,000 meters, so it's very hard to be up there, not much oxygen. It's in a very remote northern part of Chile in the foothills of the Andes, exceptionally dark skies, exceptionally spectacular geological formations, volcanoes mostly extinct, hardly any vegetation because you're so high up. It's a stark moon-like landscape, silent, remote, desolate. No people live there. Very few people live there. I shouldn't say none. There are some native Andean peoples who still actually live there and herd there and even farm in little places there where there's water. But that would be my first choice.
The next question is from Jan Campos, who asks, a recent study from the Japanese VLBI puts our solar system 2,000 light years closer to the center of the galaxy than we originally thought. Is this more because we just have a more accurate picture of the galaxy, or is it because of movement in the past years from us spiraling into the center of our galaxy?
Right. No, it's a good question. No, nothing dramatic is happening to the solar system in our region of space in the solar neighborhood. This was a recalibration of a distance measurement that we used to measure the scale of the galaxy. It turns out not to be trivial to measure the distance to the center of a galaxy. We can measure the distance to nearby stars extremely well by trigonometry, parallax, and that gets us out to, with modern measurements, out to a couple of thousand light years, or certainly with accuracy hundreds of light years, and that encompasses a lot of stars, but that's just a small fraction of the 100,000 light years size of the Milky Way. So to go beyond that, we actually have to use secondary methods, and they're just not as accurate because they depend on the properties of particular types of stars, typically variable stars like Cepheid variables or R. Lyrae variables. And one of the complication factors in looking at the scale of the Milky Way is that we're in the Milky Way, in the disk, and there's a lot of dust and gas in the disk of the galaxy, and that dust and gas reddens light and extinguishes light. So when we look at stars towards the center of our galaxy, for example, we're looking through a lot of dust and extinguishing material, and you have to be able to take out the effect of that dust before you can actually use any method to calculate a distance. And it turns out that there have been systematic errors in these calculations that have been uncovered with other methods by using more than one method, for example, and that's led to a re-estimation of the distance to the center of our galaxy.
And the next question is from one of our live viewers who would like to know more about tidal effects. I think I understand why the moon always shows the same face to Earth, but I don't understand the behavior of Mercury. Can you talk a little bit about this?
It's the same phenomenon. So tidal locking happens anytime an orbiting object is relatively close to the object that it's held by its gravity. So the gravity of the Sun on Mercury, the gravity of the Earth on the Moon. When these objects are relatively close and relatively large compared to the object they're orbiting, then the difference in the force between the front side and the back side of the planet or the Moon will essentially put a lock or a hold on that planet and therefore make them pivot around the object with the same face always pointing, and that's tidal locking. And so it happens very easily with the Moon because the Moon is such a large satellite of the Earth, and it happens relatively easily with Mercury because Mercury is so close to the Sun compared to any other planet. But it's a general phenomenon. It can happen in any situation like this.
And the next question is from Andrew Downey. Sir Patrick Moore once strongly advocated the value of amateur backyard astronomy as perhaps surprising yet powerful means of discovery and new knowledge. Does this still hold validity outside of citizen science initiatives? In other words, are observations or astroimaging used really useful using readily obtainable amateur telescopes?
Definitely. And the real innovation has not been in the telescopes themselves. The optics of amateur telescopes have improved slightly over time, and they're now cheaper, high-quality plastics that mean that you don't have to use glass, and the cost of amateur telescopes for the same quality has actually gone down. But the real innovation is the detectors. So it used to be that amateur astronomers just looked through their telescopes with their eyes or maybe attached their camera and took photographs. Well, now with digital imagers, the digital imagers, especially those that don't need any cooling or use a photoelectric cooling and so don't need a cryogen like liquid nitrogen, the cost of those cameras has come down dramatically. I think the cheapest of these cameras and the smallest of them is less than $100. But for a few $100, you can get a very reasonable one, and for $1,000, you can get a really high quality one of a large number of pixels. So the quality of the equipment amateur astronomers are using to register the images, CCDs, essentially small, less high quality versions of the research grade CCDs astronomers use at big telescopes, that's transformed amateur astronomy and the ability of amateur astronomers to do scientific research with their telescopes, to produce publishable results, to be parts of networks that are following objects over time. in addition to doing citizen science, which they can also do.
All right, it is now 1:59, and I think this will be, we have time for one more question, and then we'll wrap up. One of our live participants has asked two separate questions that I'm not sure that they realize are connected, but they'd like to know, why is it that quasars, they also asked about why active galaxies emit particle jet streams from both sides, from the north and south poles of those objects.
Right, so active galaxies, which include quasars are just the most extreme form of active galaxy, where the mass of the supermassive black hole is large, maybe billions of solar masses, and where the luminous output of the quasar essentially dominates the light of the galaxy that surrounds it. And so from a distance, all you see is the point of light, hence quasi-stellar object, quasi-stellar radio source. But active galaxies do this too. That's the more general term that might include Seyfert galaxies and radio galaxies. It's a general phenomenon that if you have a gravitational engine, which is the supermassive black hole, which is essentially converting gravitational potential energy into radiant energy through an accretion disk, and the accretion disk forms in the equatorial plane of the spinning black hole, because the black holes have angular momentum, and that tends to create a low density region away from the equatorial plane at the poles of the black hole. And so there's a natural process whereby ambient material, which is plasma, so the gas is very hot, so the electrons have been stripped from the protons, where that plasma will preferentially flow away from the quasar, or the gravitational object, along the poles. Now, why does the material flow away and not just fall into the black hole? Because there's a black hole there. It's simply because the gravitational pull on that plasma is exceeded by the radiation pressure from the already hot material near the black hole. And so that plasma is just driven away by radiation pressure, which exceeds the gravitational attraction by some large factor, actually. And so you have a very efficient acceleration mechanism along each of the poles outside the black hole, and that accelerates the plasma particles to high fractions of the speed of light, 99.999% of the speed of light. So it's a relativistic plasma, and they call them relativistic jets. And as seen from afar, those can be quite spectacular objects. If you're looking down the beam of a jet that's moving close to the speed of light, you get relativistic boosting of the radiation, which can make it seem brighter than a transverse jet would appear by factors of hundreds or thousands. So that's why quasars and relativistic jetted objects can be quite spectacular to observe. But it's a pretty general phenomena of a supermassive black hole surrounded by an accretion disk at the center of a galaxy. That was a good question to end with, something we don't always talk about. So thanks again for your participation today, and we'll be back with you next week and then take a little break for the holidays.